Okay. So, good afternoon or good morning, depending on where you are. I don't know. I guess all of you are already living the afternoon. So, what I'm going to do is to summarize and to tell you about the second chapter of this book. And this second chapter deals with complexification and real forms. So I'm going to start. Can you read there?
Yeah, that's fine.
Okay. So I'm going to go slowly. I'm going to start with a real vector space. I am calling it V naught. This is a real vector space. The way you define the complexification is by performing the following definition, or by introducing the following definition, where I is the imaginary unit, right? So then this thing here is called the complexification of V naught. And it is a C vector space, okay? Moreover, you have that the dimension of the complexification of V naught as a complex vector space is equal to the dimension of V naught as a real vector space. Why is this? Because if you take a basis of V naught, and our basis for V naught will be also a C basis for V naught C, the complexification of V naught. And conversely, if you start from a complex vector space, then you can regard V also as a real vector space, okay? Just by forgetting how to multiply by complex numbers. You can regard V as VR, a real vector space, or and VR is called the realification of V, okay? So what you have here is just, well, you have here like two operations. If you start from the vector spaces over the real numbers to this side, you can do, yeah, the complexification. This you can write also like this is a tensor product. And you get a complex vector space. And you have an inverse operation to this process, which is the realification. Indeed, this is an example of a pair of adjoint functors for those who know about category theory. But I am not going to give details about that. Okay. So the first thing that I want to tell you is the following. is this lemma. Take a real vector space, V naught, and take its complexification. Okay? Then if you have a real map, a real linear map, phi, then this map extends uniquely to a C-linear map on the complexification. This is, we can, well, our linear map extends uniquely to a C-linear map, let's call it phi sub C, which is defined in the complexification and is a C-linear map. Okay, why do I mean by extend? Well, what I mean is that the following diagram maybe here I put a different vector space because it's not necessarily an endomorphism. And here, sorry, this is like this, phi sub C, BO prime C, okay? And this diagram is commutative, okay? This is what it means that phi C is extending phi, okay? So I'm going to prove this, or to sketch it. It's very easy. So what you have to do first is to construct phi sub C out of phi, okay? You have to define the map phi C. How do you do this? Well, VO plus IVO was equal to VOC, right? So you have to define what's the image of a sum like this. So you define phi C in the natural way, okay? Where V and W are V naught. I am proving these things and I am going a bit slower than in the book because, well, there are some typos in the book. I would like to warn you about this. For instance, in the third line, I don't know if you have the book in front of you, but in the third line, the dimension is mistaken, and also this mapping that he defines as the complex conjugation doesn't make sense. It's not well defined. If you want to fix this, maybe you don't know what I mean. Sorry, I'm going to write what Onishchik is doing. This is not completely related with the things that I'm telling you now, but so he says that for an arbitrary complex space V, then you can always define this map U minus IV, where U and V belong to V. Okay, but this is not right. Okay, this doesn't make any sense because this is not even well defined, right? So yeah, this is a mistake that happens a lot.
Yeah, probably he meant the complexification, right? That you're performing. Yeah.
The way to fix is if you put here V naught and you take V not to be just an arbitrary complex vector space, but the complexification, then this makes sense. Okay, this is the way to solve this. Okay, so it's more of a typo, but can be very confusing because this is an important thing. When you take an arbitrary complex vector space, there is not a canonical complex conjugation, let's say. Okay, but I will continue with this. So I was trying to prove this lemma. And yeah, so the first thing you have to notice is that phi sub c satisfies the diagram. Okay, this is immediate. And then you have to prove that is C linear, which you can also do. It's just a computation. And then you already know that for every R linear map, you can construct a complex linear map defined on the complexification. And to prove that it's unique, what you have to do is to notice that if you have a different map, let's call it phi prime C, satisfying the above diagram, well, this means that phi prime C of V is equal to phi C of V for every B in V naught. Okay, but yeah, if this map is C linear, then you conclude that phi C prime is equal to phi C. This is because C linearity of phi prime C. Okay, and this proves the lemma. Okay, let's call it lemma 1. It's everything clear so far?
Yeah, it's perfect.
Okay, so yeah, I will continue with real forms and real structures. Real forms and real structures. So now you start with an arbitrary complex vector space V. And yeah, I'm going to define what is a real form. So what is a real form? W is a real form of V if it is a real subspace of VR, the realification of V, such that V is equal to W plus I times W. Okay? This is a real form. Another useful definition is the following. Real structure S of B is a C automorphism satisfying the following conditions. The first one is that it takes out the sum of vectors. Yeah. The second one is that if you multiply by some complex scalar, some complex number, you have to conjugate if you want to take this scalar out.
Shouldn't then be an R automorphism, not a C automorphism, because kind of C implies that it's C linear, no?
Yeah, you are totally right. It's a R automorphism of VR. Yeah.
Yeah, cool.
You're right. And the third condition is that the square of S is the identity of V Okay, this is what is an involution. This is said to be an involution. And one R automorphism of VR satisfying these two properties, or not necessarily an automorphism, but just a linear map, is called an antilinear map. Okay. Or maybe we can say C antilinear map to be even more informative. Maybe I omit this C in the future. Okay, so it turns out that these two definitions.
Doesn't the first condition automatically follows from S being a real automorphism of B regarded as real space?
Yeah, that's true. That's true. That's true, but I wanted to write it down for completeness, or but it's true. It should follow for. Maybe there is some issue there because you don't you have a map here. It's a very subtle thing, but I think you are right. You have a map here in VR, okay? And if you want to consider now a map of B, this is a different map because it doesn't have the same domain. So somehow the natural way to induce yeah, essentially I think you are right, but just to be safer, we can put it as a condition. You understand what I mean, Tomás?
Yeah, I was just being picky.
Yeah. Okay, so let's go. So I was telling you that these two concepts are related. And not related because there is a one-to-one correspondence between real forms and real structures. So I'm going to prove that. So the set of real forms is in one-to-one correspondence with the set of real structures of V, real forms of V, real structures of V. So we start from V naught, a real form of V. Yeah, this is a subspace of V. And I will show you that you can define a real structure, which is a map from V to V, which I'm going to call SVO, okay? If you go on the other direction, you start with a real structure of V. What you have to do is just to take the set of fixed points of S. And this is going to be a real vector subspace of the realification, and it's going to be a real form, okay? So this was more or less the proof already, but I'm going to write something. So you start with a real form of V. So V is equal to complexification. And you define SV naught as this map, which takes this element into this other. And here, U0 and V naught belong to V naught. Okay, this is really important because it's easy to get this mistake that I was mentioning at the beginning, that the complex conjugation is somehow canonically defined in a complex vector space, but no, you always need to specify a real form, okay, in order to to have a good definition of a real structure. Okay, so, well, you can check that SB0 is a real structure. This is an easy thing. You have to check these three conditions. And on the other hand, if you start from a real structure S of V, as I was telling you, fix S is a real form of V. Okay, and you can also check this very easily. You just have to prove that V, the set of fixed points, plus I times the set of fixed points is equal to the whole vector space V. And moreover, these two processes, I start first with the real form, then I consider the associate real structure, and then I consider the set of fixed points of this real structure. Well, these two processes this is one way to see this composition of maps, right? And the other way is you start with S, a real structure. You look at the set of fixed points of S, and then you look at the set of, the real structure associated with the set of fixed points of S, okay? And you can prove that this is equal to S. What you have to do is to use lemma 1, right? Because you have now two maps, S and S fix S, right? And you know that they coincide in the real form, so by uniqueness they must be equal, okay? So this is the proof of the proposition. You have a one-to-one correspondence between real forms and real structures, okay? Good. So now I'm going to tell you something about geometry. So this is not in the book, but I think it was interesting to mention it. If you don't like it, you can tell me to skip it. So this is an example. So what I'm going to tell you is how the set of real structures on CN looks like. Okay. What do I mean by this? Well, this X, the set of real structures, can be given a structure of a homogeneous space. Okay. So it turns out that X can be identified with this coefficient. Okay. You have the quotient of these two Lie groups. So how do you prove this isomorphism? Well, first, you consider the action of GLNC in X in the following way. You have an element G, a matrix with complex entries and determinant different from 0. You have a real structure in X, and what you do is to conjugate, okay? And because of C-linearity, this is again a real structure. And also because S was an involution, this is an involution, so yeah, this is a real structure. And you can prove that indeed it's a well-defined action. Okay. And I'm going to show you that the GLNC acts transitively in X. Okay. So how you prove this? Well, you have to find for two elements in X, one element in G, such that G of S is equal to S prime, right? This is what you have to do. So, well, what you do is you pick a basis for S for the set of fixed points of S. So you expand this with some basis. Yeah, and now you have this property that if you are given to, well, these are R bases of this subspace, which, remember, lives inside here, the realification of Cn. But they are also complex vector bases of Cm, okay? Okay, so it turns out that for every two different C bases of Cn, there is an element of GLNC which maps one basis onto the other. So there exists some element G in GLNC such that G of Vj is equal to Wj for every j between 1 and n. Okay? So you have that G of this vector subspace. Sorry, not yet. You have that G of S restricted to the set of fixed points of S is equal to S prime G restricted to the set of fixed points of S. Okay? Okay, so then you have that G of S, G minus 1 is equal to S prime, right? Because what I'm using here is, again, the uniqueness of lemma 1. Okay, because again, I have two R-linear maps which are the same on some C basis of Cm. And then there is a unique extension, okay? So I have proved that this action is transitive. And now I am going to compute the isotropy at some specific point of X, some real structure on Cn. So what is your favorite real structure of Cn? The standard complex conjugation. How this is defined? Is defined in the following way. You take Cn, you take a vector, and what you do is you complex conjugate the coefficients of the vector, okay? And this is called the standard complex conjugation. Okay? And of course, this is a real structure of Cn, so it belongs to X. So we want to compute the isotropy at this point. So GCG minus 1 is equal to C. This means that phi is in the isotropy. Well, you can prove that this is equivalent to the condition that G bar minus 1 is equal to the identity of Cn. How do you do this? Well, you have to write out this in terms of matrices. So you have to, for instance, you take the canonical basis of Cn, and if you make these computations, you realize that this is the same as this equality is the same as this other equality. Okay, but this is equivalent to the fact that G is equal to G bar. By bar here, I'm meaning that the associate matrix, what I'm doing is I am conjugating, okay, the entries of the associate matrix. But this means that G lies inside G, L, and R, okay? Because, yeah, if a number is equal to its conjugate, if a complex number is equal to its conjugate, then it's a real number, right? Okay. So then you have that the stabilizer of the action GLNC at phi is equal to GLNR, and since GLNC is acting transitively, then X is equal to GLNC mod GLNR. Yeah. And this somehow is again telling us that we have to be careful. We have to be careful because there are many complex conjugations in a complex vector space. There are this number of complex conjugations. I don't know if you like the example. Okay. Good. So yeah, I'm going to keep with this idea and to talk a very I'm going to talk about symmetric spaces for a moment. Okay. So yeah. Good. Instead of considering the GLNC action over this set X of real structures on Cn, I am going to consider another action. Okay, I'm going to consider the action by conjugation, but this time by UM. Okay, and now I am not considering just real forms in Cn, but I'm considering those real forms in Cn preserving the standard Hermitian inner product. Okay, so when I act on this set of real forms of Cn preserving the standard Hermitian inner product. Okay, so what you can do is to prove that this is isomorphic to UN mod ON. Okay, and this is now a symmetric space. It's a symmetric space because you have this map. For those who know about symmetric spaces, okay, which I think is everyone, by the way. So you have this map, and this map is going to induce you the Cartan involution in the level of at the level of Lie algebras. Yeah. So this gives you also the geodesic symmetry. Yeah. And inside of this, we have this other set of real forms. Now the set of real forms of Cn, preserving the standard Hermitian inner product and also the complex determinant. Okay, so the determinant that it has as a C-linear map. You take the metrics and you compute the determinant. Yeah, and
sorry, doesn't it mean like the fact that they preserve the standard Hermitian inner product basically means that these real forms lie in UN, which they can't because they're not C-linear. Shouldn't it be preserving the standard like Euclidean product?
Let me. Can you say again, please?
If the fact that that these real forms should preserve the standard Hermitian inner product is equivalent to saying that they lie in UN as maps of Cn to itself. But every unitary map is C-linear, which a real form cannot be.
Yeah.
So maybe they preserve the Euclidean inner product, which is the real form of the Hermitian inner. Sorry, the real form.
You're saying that if they preserve the Hermitian inner product, they automatically are C-linear? Is this true?
Isn't it the definition of preserving the Hermitian inner product?
So you can extract that from the definition. That I don't know. You have the Hermitian inner product. I mean, just this by preserving the Hermitian inner product. You say that with this is enough to conclude the A is C-linear. Maybe it's true because if you take a basis.
Yeah.
So yes, probably you're right. So here I have to say Euclidean. Sorry, to be honest, I didn't have much time to prepare this.
No, it's fine.
Okay, yeah. You're probably right. I have to look up at this.
Mm-hmm.
Yeah. Yeah, okay. Yeah, however, I didn't make the computation, so I didn't actually check this. I only did this case, the case where you just consider real structures on CN. You are happy with that one, right?
Yeah, sure.
With that example, okay. At least one is correct. Okay, so this is a totally geodesic embedding, indeed, because SUN is also preserved by this map here. Okay, yes, if you know what a totally geodesic submanifold is. So I'm going to go back to the chapter. So complex structures. Yes, but you are right. I thought about that, and at the end I don't know why I wrote Hermitian, but yeah, it has to
Yeah,
be.
I think if you just take the standard conjugation, which is the standard real form, it is not. I mean, it is not. It does not preserve the Hermitian inner product. That's what I want to say. Because if you compute the Hermitian inner product between two vectors, this will be the sum of vi and then the conjugate of wi. But then if you first conjugate them and then do this will be like the conjugate of the result.
You're totally right. Now I am 100% combines. Yeah, you're right. Yeah, but it preserves the Euclidean product of the
exactly. Yeah.
Yeah.
Great.
Yeah, so very nice because I learned something else. Okay, so complex structures. A complex structure, J, is a real in a real vector space. V naught is an R automorphism such that J square is minus the identity of V naught. Okay. So just a few observations. When you have a complex vector space V, you can regard the realification VR you can regard it as the realification endowed with a complex structure, and the complex structure is the multiplication by I there, okay? And conversely, if you start with a complex structure J given in a real vector space, then you can see VO equipped with J as a complex vector space And you define multiplication by complex numbers in this way. AVO plus VJVO, okay, where VO is in VO, okay? So in particular, yeah, you need a even dimension because of this one line argument. The determinant of J, this is a real linear map. So the determinant is a real number, is a positive real number. This is the same as the determinant of J squared. The determinant of J squared is equal to the determinant of minus the identity of V naught, and the determinant of minus the identity of V naught is minus 1 to the power of the dimension of V naught. But this is greater than 0, so the dimension of V naught is even. Okay, probably you all knew this, but I like this kind of arguments because it's a one-line argument and it's a beautiful proof for me. So, okay. What else? Complex conjugation. So we are going to mention the complex conjugate vector space. So for any C vector space V, we define V bar, the complex conjugate, where multiplication by complex scalars is given by, so we have a complex scalar, and this is the new multiplication in V bar. And what we do is the old multiplication, but we put C bar here, okay? And we do this for every scalar, sorry, what is this? For every complex number, okay? So I'm going to prove a lemma concerning this. Every C linear map what the fuck? This doesn't make any sense. Ah, yes, it makes sense. It's a C linear map. In this is a C linear map, alpha bar, V bar, W bar, okay? And moreover, if alpha is expressed by a matrix A, then alpha bar is expressed by this matrix, the conjugate matrix, okay? And 2, if you take an antilinear map, okay, remember that this meant that well, the map respects the sum of vectors, but if you multiply by some scalar, you have to conjugate, okay? Can be interpreted as a C-linear map from V to conjugate of W, okay? So, well, some small how do you say this in English? The small comments on this. So, well, yeah, to me it happened that through a long time, I thought that the good linear functions were the C linear functions, and also I thought that the good functions defined in C were the holomorphic functions. But then I realized that there is all this wall of anti-holomorphic functions, which essentially they have the same properties of the holomorphic functions, but they are not usually studied. Okay, they have the same kind of regularity properties and all this kind of stuff. I don't know why they are not that studied, but yeah, the thing is that there is just a very subtle difference between these two concepts. So somehow this lemma for me was clarifying because, well, it's telling you exactly that if you start with an antilinear map, well, this is just a C-linear map where you have changed the way of how you are multiplying the complex numbers. So it's very similar after all. So there is like a symmetry, right, between these holomorphic and anti-holomorphic settings. Okay, so let's go with this. So I start with a C-linear map, and I wanted to prove that it induces a C-linear map on the complex conjugate of the underlying vector spaces. So let's call it alpha bar, this new map. Now I multiply by some vector v. This is equal to alpha c bar v. And now here I just use the definition of the multiplication. And now what I am using is that this map is C-linear. So this goes out. Alpha is C-linear. And now I use again the definition of the new multiplication on V bar. So this is C star alpha bar V. Okay? So this is the first part of one. And then for the second one, I have to pick a basis. So let Vj V, well, and Wj V basis. For V and W, respectively. So then alpha Vi is equal to, I'm going to express it as a linear combination of the coefficients of the matrix Wj. But now if I make alpha bar Vi, this is equal to Aij, and now I have to use this other multiplication. Okay, so by definition, this is Ij bar Wj. Okay. Well, for the other one, imagine that we call it alpha, this antilinear map. So we have that alpha C star W is equal to what? Well, this is alpha of C bar V. I am using the definition of the new multiplication, and now this map is antilinear. So I have to conjugate twice. Okay, C alpha B. So at the end of the day, I get C alpha B. Okay, so I get a C-linear map. Good. This was lemma 2. Yeah. Are you still there? Are very bored? Can you tell me something? because yeah, I cannot see anybody because yeah, I am not used to this kind of stuff of writing on a whiteboard without anybody there. Are you there?
We can see it perfectly.
Yeah.
We can
You can
sometimes copy everything.
Okay. And how it is so far? Have you have any question, comment?
No, I think I mean it's clear to me at least.
Okay. Okay. The rest of the people?
It's fine with me too.
Okay. Okay. Well, at least the people answer.
Can I probably ask just one small question if
yeah,
you go
please,
back to
please, this is the idea. Yeah.
The small question, if you go back to this quotient by like UN by ON and so on.
Good.
What was so you defined the space that is represented as UN by ON, as we've now figured out these are real forms that are orthogonal with respect to the yes. What is then? Can I just look SUN by SON? So these are real forms of.
Yeah, you need that they preserve the complex determinant. Well, that's actually a guess because I didn't make the computations. I must confess.
The complex determinant, right? Yes.
Yeah, this is a guess, but probably is the real determinant of the realification now because based on what you said. But this was just a guess. So what I'm meaning here by real determinant is that when you have a matrix, right, a complex matrix, yeah, you can express it as, well, this is not a good notation, but no. You can express it as A1 plus I V1, right? And yeah, then you can write this matrix as I1 minus B1, B1, A1 probably, and this is a matrix of GLN to R because this, well, A1 and B1, I should say A1 and A2, A1, A2, A2. So AI here has real entries, okay?
Yeah, okay, so maybe it makes sense.
What you do is you compute the determinant of this thing.
Yeah,
and this is what is going to be preserved. Because yeah, I was very sorry for that. I didn't have time to make the computation.
No, it's perfectly fine. I mean, that's not. That's the additional
I think it was, to me, it was like suddenly, because I haven't told you the end of the story, but these examples somehow make sense. Yeah, I found out like a relationship between this chapter and symmetric spaces. More than the obvious reason that the isometry group of a symmetric space of non-compact type is a non-compact real form of a complex Lie algebra. So yeah, I wanted to share this with you. Maybe I shouldn't have.
No. That's great. That's basically you're showing that there are more relations between this business and symmetric spaces than just the obvious one.
Yeah.
Yes.
Yeah.
Sure. No, that's great.
Yeah. Okay. Yeah. If you don't like, say next time I will just focus on the book. But I thought that this was interesting, and I wanted to share it with you. And yeah, so I am going to. So yeah, concerning what you said, yeah, we should well maybe
I can actually, sorry for interrupting you, but I think so do you mean by real determinant
the determinant of these metrics? Yeah.
Just the thing is that I trust you I trust you that the SUN by SON is totally geodesic in UN by ON.
Yeah.
But I think it should be of codimension at least 2 in UN by ON. Just because if you have the only, or shouldn't it be?
No. Actually, you have R times SUN inside there. Well, not R.
It's a codimension 1, right?
It's not R. It's maybe a circle.
Yeah.
Or a quotient of this product. Yeah, but If you go to the non-compact setting, yeah, you.
Yeah, it's just that you have
no. You're right.
You have a hypersurface which is totally geodesic, and usually like totally geodesic hypersurfaces are kind of a rare thing.
No. Of course not. You are totally right. Yeah. This thing doesn't make any sense actually. I don't know why I thought this. Yeah. Bah. Sorry for that.
I mean, I think we should just figure it out and then
Yeah.
clarify the next time.
So next time I will tell you. Next time I will tell you how you. Yeah, but
sure.
yeah, of course it's not a total US exam manifold because it has codimension 1. Yeah.
Yeah, I need to check it.
Yeah. What is
just
a total US exam manifold is this. Yeah. You're right.
Yeah, okay, so sorry for like lingering in this. I think we should just.
No. But you are totally right. This. Yeah, we have to forget about. Well, this is true. Okay. The thing is that. Well, still. No. I think I was correct. Okay.
Maybe because
So,
UN by ON is not a symmetric
it's not
space.
an irreducible symmetric space. Yeah. No. I sorry, because I am
so
looking
much
like
confusion.
crazy.
Sorry about that.
I am looking like crazy, but no, I think I was right. Yeah. I think this is a total US exam manifold. Now you make me feel confused because but no, I think it's right.
So my argument was that the only symmetric space where you have a totally geodesic hypersurface is RPN and RHN.
That only works if it's irreducible, of course.
Not even that, but like UN by ON is not a symmetric space, isn't it? It's more like
I think it is. I think it is because of this, because you have this map here, and this will give you a geodesic symmetry. About that, I am really confident.
Okay.
I think, yeah, so the non-compact dual of this will be R times SLN R mod SON, okay?
Well, it's not non-compact.
This is non-compact.
It's not semi-simple. There's no duality when you have
there is not, but well,
yeah, I mean, it's not. So what you mean is that it's not a symmetric space of compact type, or rather, it's a symmetric space of compact type and also one circle.
Yeah.
Yes.
It's dual, but this dual is not unique. I mean.
Yeah. Okay, fair enough.
If you go in this direction, in this direction, you can have multiple covers. You can have very strange stuff. But it's the non-compact dual in that sense. The non-compact duals of this compact, yes, is unique because there is not another. Do you understand what I mean? Yeah.
Yes, I do.
Yeah. So yeah, I think this is right now. But next time I will thoroughly check, and I will tell you about it. Okay.
Okay, great.
I don't know if you like this thing or you think that is not very interesting. What the other people think about this? Tomás, what do you think?
I mean, I think I also have to think about it.
Yeah, but do you think that it's interesting to look at this and
sure.
I told you about this? Okay. So I will. Okay, so yeah. So we were talking about. We were talking always about linear algebra and vector spaces, but now we are going to talk about Lie algebras. Okay. So the complexification of a real Lie algebra is defined as follows. This is the underlying vector space. So this is a direct sum of vector spaces. And now you define a bracket here in this way. This is the obvious way to define the bracket. So x1 with x2 plus or minus, sorry, minus y1, y2 plus I times plus yeah. Okay, so the idea is that all the concepts that I have defined can be redefined again by adding the word Lie algebra conveniently. Okay, so there is just one which for me is not that obvious to define what a complex structure is on a real Lie algebra. Okay, and this is true for every element in G0. Okay, so this is a complex structure of GO. It's a linear map J such that it can also go to the first position in the bracket, but yeah, okay. And oh, of course, J square is minus the identity. Okay, so let's go with this proposition. So yeah, I told you about real forms of complex vector spaces. So now you can consider real forms of complex vector spaces. Okay, so we have two real forms of a complex Lie algebra G. And I'm going to denote by sigma O, sigma 0, and sigma 1 the corresponding real structures. Okay, and remember that there was a one-to-one correspondence between these two things. Okay, so the proposition says that GO is isomorphic as Lie algebra to G1 if and only if sigma 1 is equal to this for some alpha, which is an automorphism of G. Okay, and this is a complex linear automorphism. Okay, so how do we prove this? This is telling you that up to this transformation, real forms are unique on complex Lie algebras. Okay. And somehow we have already proved this when I did the example, because this is like a very similar thing, right? We are saying that the two real forms are in the same orbit, right? If they are isomorphic, right? You can consider the group of automorphisms of G acting by conjugation on the set of real structures, and the underlying real forms are isomorphic if and only if they are in the same orbit. I just realized that. I think it's interesting from the geometric viewpoint. So alpha, an isomorphism of Lie algebras. Okay. By lemma 1, there is a unique way to extend this to complex, an isomorphism of complex Lie algebras. And since they are real forms, this is going to be an automorphism of G. Okay, so we have the following diagram. G1, this is a real form, this is inside G, this is inside G. Okay, alpha, alpha C. Okay, and this diagram is commutative. So it follows that alpha C, composition sigma 0, and alpha C, composition, well, first we compose with sigma 1, are anti-automorphisms. Okay, and they coincide in G naught. Okay, so as I told you, when you have an anti-automorphism, it's like if you had a automorphism somehow. Okay, and then we apply this lemma 2 that I prove that allows you to make a complex automorphism out of a anti-automorphism. Okay, so then you can use these two lemmas, lemma 1 and lemma 2, to prove that these two are equal. And why they are equal? Because they coincide on the real form associated to sigma O on G O. So alpha C sigma O restricted to G O is equal to sigma 1 alpha C restricted to G O. So this implies that alpha C sigma O is equal to sigma 1 alpha C. And then we already have it, right? Because sigma 1 is equal to alpha C sigma 0 alpha C minus 1. Right? Yeah. Okay. So this was the implication to the right. Now, for the other implication, we assume that we have this thing. Yeah, if we have this equality, this is the same as this. And now this implies that the set of fixed points of sigma O, well, the image under alpha of this subspace is equal to, well, is contained, but by dimension reasons it has to be equal to the set of fixed points of sigma 1, okay? Thus, alpha restricted to G0 to G1, this is an isomorphism of Lie algebras, which is the other implication, right? So this proposition is going to be very important for the rest of the book. And yeah, I have used it in, well, I have used all these things in the work that I was doing with Andreas, that Ivan was yesterday at the talk, and he watched it. So okay. So I'm going to finish with this relationship that before of that, yeah, I still have 15 minutes, right? So I'm going to define what is a quaternion first. So what is a quaternion? A quaternion is an element of the form Q equal to Z plus GW, where Z and W are complex numbers, J squared is -1, and J -1, this is just the conjugation. So the conjugation by J is the complex conjugation, okay? And we denote the skew field H, well, the skew field of quaternions by H. Okay, so what is a quaternionic structure? So a complex structure was something that you define on a real vector space. So now a quaternionic structure is going to be something that you define on a complex vector space, and it's going to be the following. It's going to be the following. It's going to be an anti-automorphism of a complex vector space such that its square is minus the identity. Okay, so in particular, it does not commute with the complex multiplication. It anti-commutes with it. Okay, so if you have a quaternionic structure, okay, what you can do is the following. You have your quaternionic structure, right? Of B, a complex vector space. So now you can think about the realification of this complex vector space V. So now J is a complex structure of VR, okay? And it's a complex structure of VR that anticommutes with the complex structure of VR induced by the complex multiplication also, okay? Good. What else can I say? Yeah, also to be consistent. If you have a complex vector space equipped with a quaternionic structure, then you can see this complex vector space as a quaternionic vector space. Well, maybe this is not an accurate thing to say, but well, some people talk about quaternionic vector spaces, but traditionally, I always have been taught not to say quaternionic vector space because they are a skew field and not a field, and then you should say the module, a module over the quaternions, or yeah. Okay, but I will say quaternionic vector space because for me it's easier or more natural. And how do you do this? Well, if you have a complex vector space equipped with a quaternionic structure, you are going to define a multiplication on the right, okay? So I take here C plus IW. Is this the good notation? J, sorry, JW. And I have here an element in V. This is an element of the quaternions, right? So how do you define this? Well, what you do is set V here. Is this right? Let me check. Yeah, it's right, because yeah, multiplication here is commuted. And now you do WJ WJV. Okay, so that's how you defined the quaternionic multiplication now on this complex vector space. So as an exercise, prove that the complex dimension of V is even. Okay, as a complex vector space. This is an exercise. I don't know how to do it indeed. This is something that I was thinking while I was writing the notes. If I could have a one-line proof, as I showed you before, about the dimension of a real vector space admitting a complex vector structure. So what I want is a one-line proof of the following: that if you have V and a complex vector space, and you have J, a quaternionic structure, then the dimension of V is even, the complex dimension of V. Maybe this is really, really easy, but I didn't have time to prepare it because, yeah, I didn't have time. Sorry for that. So maybe some of you already know how to do it. If that's the case, please tell me.
Well, a fancy way to prove it is that H is a division algebra over
Yep.
R. So every finitely generated module over it is free. So you can find a basis E1 blah 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 En, which is the basis of V as an H module, which means that the real dimension will be 4n, and the complex dimension.
Yeah, of course. Yeah, but I want a one-line proof with. I don't know if it exists, but that's yeah. Of course I know how to do this, but
But I don't think there. Maybe there is some proof which is kind of similar to what you did in the complex.
Yeah, without taking a basis and without with one line proof like the other one. I don't know if it exists, but using the determinant maybe, or I don't know. Probably using the determinant has to be something, right? Because probably the same proof applies. I don't know. I haven't think about it. Okay. Okay, so I will just finish by telling you this beautiful relationship that I realized while I was studying this. So you have the norm division algebras, right? The associative ones, okay? So we are forgetting about the octonions. What we have done is that if we started from a real vector space, we have complexified to get a complex vector space. And if we started from a complex vector space, we can also put a quaternionic structure on it to define a quaternionic vector space. And also, if we started from a complex vector space, we could get a real vector space by forgetting the complex multiplication. And you can imagine that the same you can do with a quaternionic vector space. Okay? Okay, so these are the associative, real, norm, division algebras. Okay, so now you start with classical symmetric spaces. So this is something that I discovered that is a way of this is something good. It's a way to remember all classical symmetric spaces. Okay, maybe you all knew how to do this, but so classical symmetric spaces. of compact type. As I told you, there are some coverings of them, so, well, these are all up to coverings, okay? So you have these Grassmannians. Over R, C, and H, okay? Then you also have these compact Lie groups equipped with beam variant metrics that what they do, they are defined to respect the standard Euclidean inner product or Hermitian inner product that you put on them. They are SON, right? SUN and SPN. I am not forgetting anything, right? So far, compact groups equipped with the invariant metrics. Yeah. And now you have these spaces, okay? So you have this square. So I'm going to paint it. Sorry. Okay, so you have this thing R, C, H. Are you still there?
Yeah.
Yeah, okay, because my computer started to go very slow, so I thought that maybe I lost connection. And here I'm going to paint R, C, and H. Okay. And what I'm going to do now is to forget about these blocks. So I'm going to mark them with an X. And now we are going to start with these groups, these compact groups that I mentioned. So, for instance, C. What is the group related to C? Is SUN, right? And what is the subgroup of SUN, maximal compact subgroup related to R, SON? So maybe you can already know what I'm going to do.
What do you mean by maximal compact subgroup? Like it's itself compact, right?
Yeah, all subgroups are compact. Yeah, you're right. Yeah, you're right. Yeah, it's a stupid thing. No, if you are considering a symmetric space of non-compact type, that makes sense. But this didn't make sense.
Probably it is a maximal
SON is a proper maximal compact sub. It's not unique, but
yes.
But it's one of them. I didn't know if I say A or D. I don't know. Okay, so now for this block, you start with R. The related group to R is SON, but you need to double dimension in order to fit an SUN inside. Okay. Here you do SPN. What? SPN mod UN. Here is not. Here is. Sorry. Here is UN, not the. Is this correct?
Yeah, to my recollection, it should be UN below.
It's UN. Yeah.
Maybe it can be somehow explained like this space should be the space of orthogonal complex structures.
Yeah, that's precisely what I'm going to tell.
Oh, okay, sorry.
don't you are okay. SU to N mod SPN. This is the last one, okay? And these are all classical symmetric space of compact type up to coverings. Okay, essentially these are all. Okay, so I think when you learn this, you will never forget the list of classical symmetric spaces of compact type, because now the real structures of CL living invariant the standard Euclidean product and leaving also the real determinant invariant is SUN mod SON, right? This was this space that we were talking, right? Mm-hmm. So this is the space of real structures of Cn leaving invariant the standard Euclidean inner product and real determinant. This is my guess, but I'm confident now with this. Also, we have SU2M mod SPN, right? And this is now the set of quaternionic structures on C2N, preserving the Hermitian inner product. Maybe here with Hermitian I can mean the well. Now here I think it's clear that is the complex one, right? Hermitian complex.
I mean, by analogy, if above they should preserve the Euclidean product, then here they should preserve the Hermitian product.
Yeah, but if you mean the quaternionic Hermitian, right?
No, I mean, so if you're looking for real structures on Cn, but they only should preserve the real Euclidean product, then by analogy oh wait, here it's the opposite.
Yeah, it's the opposite.
Well, like I mean the real complex analog of this is SO to N by S by UN.
Yeah, that's right.
And those are complex structures preserving which are orthogonal, which are orthogonal with respect to the Euclidean product.
Yeah. Okay.
So I think here
I will write that down. So can you say again SO to N? So let's see if it was the same that I had in mind. I said these are the complex structures on R2N preserving the Euclidean product and the orientation.
Oh yeah, and the orientation. That makes sense.
Okay.
Yes.
So you call this orthogonal real structure, orthogonal complex structure, yeah. Right? Orthogonal
which
complex
are orientation preserved. Yes.
Preserving the Euclidean. Well, this is what it means to be orthogonal, preserving orientation.
Mm-hmm.
Okay, and the last one is SPN mod UN. And now I have between commas, I say complex structures on HM, but now I mean exactly the same analog of real structures of CN. Yeah? Do you agree with me on this? Complex structures on HN, preserving the Hermitian inner product of HN.
Yeah, I'm a bit hesitating because, in the case of real structures of Cn, you have, if you write your complex space as Cn, then there is an obvious way to look at it as the complexification of something. It's just Rn, and then you have.
Yeah.
Here you have like the two-sphere of complex structures, not just one unique complex structure.
Yeah.
So it may be not. Maybe you need to add something and not just. But again, I mean,
Yeah. Okay. Yeah.
I trust you. I trust you more on this because I haven't really looked.
Yeah.
Into it.
This is because it's in commas, because I don't really know if what I'm telling you is complete bullshit, but.
No, it's something like this, like maybe modulo 1, like small additional remark that maybe they need to preserve something.
Yeah. I didn't have time to put it in a finer way, but I like the picture because
and
it's like all what I told you really, fits on the way to define classical symmetric spaces of compact type. Okay. Yeah. So yeah. Well, just to mention, maybe you already realize, but if you wanted to prove this carefully, which I haven't done it, the strategy is the following. First, you consider the action always by conjugation. I think you always are going to need that action. Consider the action by conjugation. Okay, then proof that it's transitive. And then what you have to do is to compute the isotropy at some well-known element. Oh, what? Sorry. Now I'm lost in this space. Compute the isotropy. Oh. At some well-known element. For instance, when I did I didn't do this, but I did this, but without considering the Euclidean inner product and the real determinant. The element that I chose was the standard complex conjugation, because otherwise it's harder to compute the isotropy. Okay. So yeah, I leave you with this picture, and yeah, this is everything I wanted to tell you today. So thank you very much for your attention and for your comments. Thank you very much.
Great, thank you.